In the previous tutorial, we constructed a metagraph for MNIST classification task with two nodes, a feature extractor node and a classification head node. In this tutorial, we want to show you how straightforward it is to create complicated deep learning architectures using metagraph construct. Different from the last tutorial that the metagraph takes a single input in the form of images with channel size of 3, the metagraph here takes two inputs. The first input is images with the channel size of 3 and the second input is images with channel size of 4. Therefore, we need two feature extractor nodes. After adding these two feature extractor nodes, we want to add a fusion node that takes the feature maps generated by these two feature extractor nodes in order to augment the generated features to do a better classification task. We start by making a copy of the metagraph created in the previous tutorial and saving it as FusionNet. Next, we remove the classification node because we want to replace it by a fusion logic. We are going to use the existing ResNet 34 smaller as one of the feature extractor node, and for the other feature extractor node, we want to use a ResNet 18. However, first we want to inspect the architecture of ResNet 18 graphs. In order to do so, we switch to the graphs abstraction level. As we mentioned before, we assume that the second input for this metagraph is images with the channel size of 4. Therefore, we change the input channel size of the ResNet 18 to 4. Next, we inspect the graph architecture of ResNet 18. We see that the feature map generated by the last stage node of this graph has 512 channels. Since we want only the feature map generated by the last stage node of this graph to be passed to the fusion node, we change the modes of the other stage nodes to internal. We add this ResNet 18 graph to our personal graph library with the name myResNet18. Next, we add myResNet18 as the other feature extractor node to our metagraph FusionNet. We change the mode of ResNet 18 to input, therefore it becomes the second input node for our metagraph. Now our metagraph has two input feature extractor nodes. The next thing that we need to add to our metagraph is a fusion node that performs the fusion logic, getting the feature maps from these two feature extractor nodes. In order to do so, we switch to the graph's abstraction level and we create a new graph called fusion head. We add two input nodes for this graph because it will have two incoming edges from the feature extractor nodes. We choose these two input nodes to be multiplexer nodes. This is because the outputs of the feature extractor nodes will be lists of feature maps, and the multiplexer nodes here will allow us to choose exact entries from those lists. For example, here the input 1 multiplexer node that gets the list of feature maps generated by the ResNet34 a smaller feature extractor node relies on its outer index parameter to choose the first entry from the list of feature map generated by that feature extractor node. Similarly, the input to multiplexer node has the outer index parameter of 0, which means that it will pick the first entry from the list of feature maps generated by Res18 feature extractor node. Please note that for both ResNet34 smaller and ResNet18 feature extractor nodes, only the last stage nodes are part of the output nodes of these two graphs. Therefore, their output lists only will have one entry. Next, we make these two multiplexer nodes to become input nodes. After configuring the input nodes for this graph, we add a node that realizes the fusion logic for this graph. We call it fusion stage. The fusion stage takes the feature maps from these two input nodes and performs the fusion logic. The fusion stage node having two incoming edges, we need to specify its aggregator parameter in order to determine how the tensors arriving on its two incoming edges need to be aggregated. Here, we set the aggregator method to be concatenation. We set the block for this fusion stage node to be a residual block. Also, the input and output channel sizes for this residual block are set to 1024 because the feature maps generated by the aggregator layer will have 1024 channels. Next, we add a classification stage node called CLS stage that takes the feature maps generated by the fusion stage and predict the class corresponding to the input images. The block for the CLS stage node will have three layers: the global average pooling layer, a linear layer, and the softmax layer. We make the CLS stage and the fusion stage nodes to become output nodes for this graph. It is because we want to surface the feature maps generated by the fusion logic inside the graph in addition to the predictor class. Now we go back to our FusionNet metagraph in order to add the fusion head node to the metagraph. Perfect. Adding the fusion head node, it performs the fusion logic internally after receiving the feature maps from the feature extractor node. Then it performs 10-way classification. What we want to do next is to add another node that takes the output fuse feature maps from the fusion head in order to perform 100-way classification. Looking into the fusion head, we see that the computed feature maps is the second output for this graph. Therefore, in the next graph that we want to design, we need to use a multiplexer node as the input in order to pick up the second entry from the output list generated by this node. We call the new graph that is going to perform the 100-way classification the second CLS node. We add a multiplexer input node and we set its outer index to 1 so that the second entry of the list generated by the fusion head node will be picked up by this input node. Next, we add a stage node with a residual block in order to further process the feature map received by this node. Finally, we add a new stage node called CLS that is going to do the actual classification task. The block of this stage node will have three layers: the global average pooling layer, a linear layer with the input size 2048 and the output size of 100 and a softmax layer. Going back to our FusionNet metagraph, we add the second CLS node to this metagraph. We make the fusion head and second CLS nodes to be the output nodes for this metagraph.